So if I go ahead and put P is equal to mv, what is the P here? Yep, momentum. And we said momentum is kind of like, momentum and inertia, there's a very good connection between the two. But it's kind of like how much, sort of like, it's like energy, sort of. It's like how much momentum something has. If you sit down, you have lost your momentum. Your velocity 0. Okay, no momentum. And you guys told me that if we have a Mack truck with a high mass, it's going to have more momentum versus a bike with low mass. It's going to have less momentum even though they're going at the same velocity. Okay. We said acceleration. What is acceleration? It's a change in velocity. Very good. Acceleration is a change in velocity. So does this make sense that if something is accelerating, okay, changing its velocity, it must also be changing its momentum? And that's kind of all this is saying. Well, sort of. Which law, I'll ask it in this form. There's all sorts of fun things. If I put up F is equal to ma, what Newton's law is that summarizing? The second law of motion. Very good. That's the second law of motion. What does F stand for here? A force. Very good. What does M stand for? Mass. And A stands for acceleration. I kind of think of this like this way. F is equal to ma. I think of it as you apply a force and the object you're applying to it will accelerate. And it will be related to its mass like this. F is equal to ma. That's how I think of it. Kind of back, a little bit backwards. Okay. So, where's the sun? Here's the sun. Right? Ooh, don't break anything. So this is the sun. So what force did I, well, a few things. Okay. Kepler's first law of planetary motion. What is the shape of the orbits of the planets? Ellipse. They are ellipses. That's right. Very good. So as something goes in an ellipse, which is kind of an oval, is it accelerating? Is it accelerating if it's going? Yes. Even if I take the same speed, the fact that I'm changing direction, I am accelerating. And so what is that acceleration caused by? The force of, starts letter G, gravity. Gravity. Exactly. Like I'm playing charades up here. Exactly. Yep. So that's the force of gravity. Now, if I drop this, it goes faster and faster and faster. You guys remember? We talked about that. So in the first second it falls, and regardless of its mass, you know, we might have some aerodynamics going on here on Earth, but regardless of its mass, it should go, after 1 second, how fast should it be going? Do you remember? 10 meters per second. After 2 seconds, how fast should it be going? 20. Picks up another 10. Just broadly speaking. So we have that force of gravity, but you guys also told me if I scoot this along, why is it going to stop? Friction. It's friction. Force of friction, which goes kind of backwards to the motion. So does it still have gravity? Yeah. So the point up here is you can have an object and it has multiple forces acting on it at the same time. Makes sense. Life is like that. Don't you have multiple forces acting on you at the same time? Yes. Okay. Yep. So the fact, and you guys were very right, is that regardless of the mass, when you drop something, after 1 second, it's going to be going 10 meters per second. After 2 seconds, it's going to be going 20 meters per second. Then 30 meters per second after 3 seconds.
I'm sorry.
Oh, goodness. The fact that it goes faster and faster.
Thank you.
You're welcome. The fact that it goes faster and faster, we call that, of course, acceleration. And if it's accelerating, there must be some force acting on it. Of course, that's the force of gravity. So momentum I put up here. Momentum P is equal to how fast something is going times its mass. Now, if the object is either spinning, planet spin, or orbiting, okay, then it has another type of momentum called angular momentum. And angular momentum is, I don't know what the variable for that is. I don't know if it's P also. But angular momentum throws in another variable. I know you guys, this isn't a physics class, right? And I'm not going to have you guys work any problems, but I kind of need you to kind of know how these fit together. Angular momentum is mass times how fast it's going, either spinning or orbiting. And the last term is R. And R is the radius. I know my V's and R's are kind of alike. Sorry about that. Okay. So, so if the angular momentum is we're going to talk about conservation here in a minute. Energy is conserved, matter is conserved, angular momentum is conserved. So if something is going to kind of have the same angular, an object, a planet is going to have the same angular momentum if its mass is constant, but do you see where if it changes, its R stands for what? Radius. Yep. If it changes its radius, let's just say its radius goes up. Mass is constant. What does volume need to do, velocity, need to do in order for angular momentum to stay the same?
Go down.
It needs to go down, exactly. These three things multiplied by each other have to stay the same. Well, what if radius goes down? What does velocity need to do in order to keep this the same?
Increase.
It needs to increase. So we have these two kind of scenarios, and I'll show you what that looks like on the next slide. But this idea of conservation of, fill in the blank, that's kind of the way life is. That's the way our universe is. That's the way the physics, the physicalness of our universe is. Things that need to be conserved include momentum, matter needs to be conserved, energy needs to be conserved. Okay. And like the slide says, you might say, well, the energy looks different. Well, it does look different. Okay, energy can be used to do work, and it doesn't go away. It was used to do work. Okay, so it's conserved, it's tracked. And we kind of count on that in our universe. So this, I guess, excuse me, I know you guys have all kind of at least accidentally or purposefully watched figure skating. It's a beautiful sport. What happens when the skater, he or she takes her or his arms and they're spinning, and what happens if they bring their arms in? They spin faster. So let's think about what that looks like. Okay, with their arms out, this was their radius, their distribution of mass started here and went out to here. So they had a big radius. Okay, so they had a big radius, a smaller velocity. They bring their arms in. Now the radius is this big. They reduce the radius. They increase their velocity. That's all it is. Okay, I think that's kind of fun. So this slide has a few things. Let's see. I think we already looked at, did I already pass terms? Because I know we talked about the sun is off center from the Earth's orbit. And I'll go ahead and remind you what I said, but we call this, does anybody remember? I'll put it in the form of a question. When it's closest, starts with the letter A, what do we call that location of the Earth closest to the sun? Starts with letter A. Aphelion, very good. Aphelion. I think I put an extra I in there. Aphelion, very good. Aphelion. Wait, nope. Darn it. There's the other one. Yep, perihelion. So I'm gonna go over here, Riley, and I'm gonna call this aphelion. Very good though. I said it starts with letter A, and you're like, oh, yes. Final answer. Don't get this wrong on the test, because it's going to be on the test.
Aphelion.
It will. I'm sorry, but it will.
When the sun is farther away from the earth.
Aphelion, yeah. And I kind of think as like if you're gonna, and I like if you're gonna unguard, you know, do like the, you know, you parry. So I don't know that, but you're kind of close. So perihelion is close. Aphelion is far away. Thank you. Final answer. So, oh gosh, does anybody remember? Well, I'll just go and tell you. But one of Kepler's laws was how a planet moves at perihelion versus aphelion. Do you remember when a planet moves fastest? Is it when it's closest? Yes, when it's closest. At perihelion, a planet moves fastest. And this is actually just an application of, we have a shorter radius. When it's at perihelion, it's going to move fastest. Okay, so that's kind of how that all works. Yeah.
So the second law would be pertaining to perihelion.
Let's
and
see,
the
equal
third
areas.
would be to the aphelion.
No, are you talking about Kepler's laws or Newton's laws?
Yeah.
Kepler's laws, there are 3 laws of Kepler's. One was the shape.
Right.
That's his first law. The second law was this one. They call it equal areas. So basically it sweeps out an equal area at perihelion. And then aphelion goes. Okay, those are equal areas. And then Kepler's third law is my least favorite, and it's like p squared is equal to a cubed. That's my least favorite. But if Kepler's third law actually kind of talks about, let's see, yeah, his third law says that when a planet is farther from the sun, what do you think? Does Jupiter move more slowly or quicker? More slowly. That's Kepler's third law. It just said that as the A increases, that's the distance from the sun, then the P increases. And they have a relationship of squared and cubed. I don't know if that answers your question. Something like that. But that's just kind of a quick review of Kepler's 3 laws of just planetary motion. So, we're good. Cool. So we said weight and mass are not the same thing, although in chemistry we often use them interchangeably, weight and mass. I know. Mass is how much stuff, kind of like how many atoms and stuff you have. And weight actually is kind of the influence of gravity acting on that mass. That's it. I'm going to pull up a little video of the International Space Station, and they have so many cool videos up there. Oh my gosh, those guys are great. Those astronauts are great. But you ever seen the International Space Station where it looks like they're floating? Yeah, we're going to kind of talk about that. The reason is the International Space Station is orbiting the Earth, right? Okay, so this kind of shown right here, this is kind of weird. This is like a crazy man with a rocket on his back. Crazy man with a rocket on his back, crazy man with a rocket on his back. And he has inserted himself into orbit. Okay, like how in the heck did he do that? Well, it goes something like this. Anything that is in orbit is actually in free fall. It goes like this. So you see where the guy climbed, he climbed this tall tower, and I don't think this can actually be done like this, but I have 2 figures to kind of show it, as if you could climb a tall tower. In the first scenario, I'll go ahead and circle it. In the first scenario, he simply kind of stepped off. And of course, that was pretty silly of him because he fell to his death. Or let's just pretend there was something there to catch him. The second one, he took a running start. Now, in taking a running start, he fell a little bit further. Okay. So kind of in taking a running start, what was happening? Well, he had a little bit of trajectory in this way, right? And then gravity kind of did its thing. Well, let's just say this brave soul, and it might be a woman, when he puts on a pack, okay? And basically, he puts on a jetpack, he or she does, that goes ahead and gives them motion in this direction. They have motion in this direction, gravity pulling down. But notice in this case, they don't fall. Okay, and then actually it can be what's called kind of a tangent line. They have motion this way, gravity this way. 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 So they're moving, falling, moving, falling, moving, falling. And kind of one way to look at it is that they fall, but they kind of keep missing the Earth. So gravity is affecting anything that's in orbit like that. To think that the people in the International Space Station have no gravity is not true. Okay? They're actually kind of in free fall, though, which is kind of creepy, too. But that's what that looks like. And that's why they feel weightless, but they definitely have gravity attracting them. Brave soul, brave soul. So there they are. This one just happens to be all women, which I thought was kind of interesting. So let me play the video here. It's got sound, I think.